steady and constant leadership to our community over the years, and has an incredibly prolific and impactful set of research over the years, with over 14,000 citations as of 5 minutes ago. You know, ranging across the whole span of computer architecture, with impact not just in academia, but in delivered products that many of you may have in your racks or on your desktop today. I'm absolutely thrilled to hear his thoughts, so please let's welcome him.
Thank you, Tim. So I know that many of you know, but for those that don't, I have family connections here. And I grew up in Santa Barbara, and my dad was actually a professor of ECE and CS. In fact, was the department chair, I think when they were one department, and was associate dean of engineering for a number of years. So, and I was a freshman here. So I can claim to be an ex-alum in any case. So. All right, so, all right, what the heck is that? Find my slides here. So, you know, as Tim was saying, you know, I've done an awful lot of computer architecture research over the years, but this seems like a broader audience, so I went with the highest level talk that I could come up with that dealt with energy. And this is, so the title of my talk is Energy Proportional Computing, a New Definition. And I'll tell you, you know, where that comes from, you know, where the motivation for that is, and then actually tell you what the new definition is, what the new metrics are, and then a little bit about, you know, why we think they might be useful in using them. So what we're looking at here is primarily looking at the problem of data centers. And you know, looking at the title, the forthcoming and past talks, you know, I want to make sure that we get the right context here. You know, I mean, data centers are what run the cloud. They run, you know, lots of the computing of the internet, and they take up a huge amount of power, right? So this is some data that my graduate student found from some acronym mouthful that I can't remember what it means, but you know, they consume, you know, 91 billion kilowatt hours. So, you know, that's a big number. What does that mean? You know, that's 34, you know, sort of medium-sized coal-fired power plants to run all the data centers. And that is growing, as we know computing is growing. And it's projected to grow to 140 billion kilowatt hours per year, you know, which is the equivalent of what 50 coal-fired power plants will do. And it goes to, you know, where does that power go? Well, it goes to lots of things that it takes to do computing, but really only about 40% of it actually goes to the computing, right? The rest of it is going to refrigeration, cooling, lighting, you know, whatever, you know, the security systems and so on. And so you know, I guess the issue that I'm going to be talking about is, you know, how do we quantify efficiency in terms of the energy that we are using for computing versus all the rest. And so some of you may be familiar with this notion of power usage effectiveness. And so this was defined a number of years ago to say, well, if I have a data center, which, let's see if I can make that do that again. This is my graduate student's cool little animation. So we have this building, and it has a bunch of computers in it. And there they are in the upper right-hand corner, and they're doing useful work. Those are little blue blobs flying off to the side, right? And so we're pumping all this power in there. So a big data center might be 100 megawatts, 200 megawatts. And they're feeding into that, and that power has to be distributed throughout there. There's you know, switches and UPSs and backup generators and, you know, power conditioners and all this kind of stuff. And of course, since you're going to pump that energy in, you're going to get resulting heat that you have to get back out again, and you spend an awful lot of energy running the cracks and chillers and all those wonderful acronyms that, you know, I mostly don't remember what they mean. You know, and, you know, of course, you've got to turn the lights on if there's going to be anybody in there, right? And then, of course, there's the, you know, what they call the IT load, the actual, you know, servers, the storage systems, the networks, and anything else that you might have attached. Of course, most data centers have very little of this stuff and lots of that stuff. Okay, So what PUE is a metric. It tries to do is say, well, of all that energy, that 100 megawatts or 200 megawatts that we're pumping in, how much of that is actually being used by the IT equipment? Okay, and so as a computer architect, I look at this as it's a ratio. It must be speed up or slow down, one of the two. In this case, it's slow down. It's how much of that total energy that goes in, divided by the energy that you deliver to the IT load, and if that's greater than 1, which it always is, you're wasting energy. So how much energy do you waste? Okay, so PUE greater than 1. Well, okay, how much greater than 1? So the first time people really started to talk about this metric, PUEs were north of 2, right? And that graph I showed you a minute ago showed that it was like 2.5, right? 40% of the energy was being delivered, to the IT infrastructure, so that would work out to PUE of 2.5. Well, it turns out since PUE got publicized and people were designing systems to try to minimize, and buildings to try to minimize PUE, these numbers have come way, way down. Okay. Now some of these numbers I don't really believe, but they're at least publishing them. Okay. So Google, is Google on there? Google's claiming 1.08, and Microsoft is 1.125, and Facebook is 1.08, and Allied Control, and I have no idea who this is, claims 1.02. I think they're lying, but in any case, so some of this is maybe magic, but at least it's clear that the trend is going down, and for some average that my student calculated or quoted said it averages 1.7, and that's a lot better than 2.5, right? And a lot of this comes about just because we had the right metric to characterize what the problem is, okay? And then once we know what the problem is, we can improve that, okay? Well, that's great, and this has been a great metric, but it only talks about the energy that I'm pumping into the IT equipment. It says nothing about how well that IT equipment is using that energy, okay? And so we need another metric that talks about how well we use that energy once it gets to the IT equipment, and that's what this talk is about. Okay, so the standard metric that people use for talking about this is energy efficiency, and that can be defined as either work divided by energy or performance divided by power. I'm going to use energy, but that's just a time constant in there. And so so the way to think about this is we're going to do some amount of work, some number of search queries or some number of database operations or whatever, but a constant amount of work, and then how much energy it takes to do that. Okay, and if we want to say over a period of time, then we get performance and power. Okay, and so we got lots of metrics that people use to talk about this: BIPs, billions of instructions per second per watt, or this is Spec power, or actually I don't remember what it stands for. Ops per watt, instructions per nanojoule, whatever. So these metrics are all equivalent. But the key thing is, so we're going to talk about this energy efficiency. That's this I always want to call it new, but it's eta, eta max. So that's the best efficiency that you can get. That's going to be equivalent to the minimum energy that you can use to do a particular computation. So we're going to see these etas and min energies through the few equations that I have in this talk. So try to remember what those are, and if you don't, ask me and I'll remind you. Okay. So we're not the first to look at this problem of using the computation efficiently, characterizing the making good use of the energy that's being put into the server. Okay. And so this was first characterized, or the work that I became most familiar with, and certainly was broadly leads in the citation counts, is this work by Luis Barroso and Urs Hölzel on energy proportionality. And so the idea that they put forth is that, well, what you would like is that the amount of energy that you put in should be proportional to the amount of work that you do. Okay? Seems like an obvious thing, right? Turns out it's not that easy to do, as we'll see in a moment. Okay, and so this is, again, we can, if you want to do it as power, well, it's just energy over time. Performance is just work over time. Okay, so our goal here is that eta should be constant. Okay, and there's a bunch of questions, about, does energy proportionality imply that you're going to get use the minimum energy for computation? Is the converse true? Are they identical goals? And we'll see that they don't. That the answer is more complex than that, or there's no simple answers to that. Okay, so the energy proportionality was motivated by an observation of server systems at the time, and so this is the sort of the motivating quote from this paper, which is that they said, we see that peak energy efficiency occurs at peak utilization and drops quickly as utilization decreases. Okay, and so a consequence of this is that you're going to waste a lot of energy if you run your servers at low loads, low utilizations, and that's bad because it turns out that if you are doing search or any other latency-sensitive workload, those servers are not very busy, and that makes sense from the standpoint of queuing delays. If you have high utilization, you can end up with high queuing delays. You're going to have poor response times, right? And so it's not uncommon for the servers to be 10, 15, 20% utilized. It's actually quite rare for them to be above 50% utilized. And so energy proportionality was, so as we'll see, this is not going to lead to energy proportionality with these properties. Okay. And so this has really been a very important metric, and I'll show you graphically how this looks in just a second. But this is really, the creation of this metric has really changed the way people build servers today, and had a lot of impact. So let me just jump ahead past that one. So I'm going to be showing you a bunch of graphs. They're very simple graphs, so they're not too hard to follow. I just want to tell you where the data for those graphs comes from. So we're using a workload called Spec Power. This is from the Spec Consortium, industry standard group that puts together benchmarks that people use for a variety of reasons. Spec Power is used for measuring energy efficiency, power efficiency of servers. And the way it works is you do some calibration to figure out what the max load the system can run, and then you run it at peak load, and then each of the deciles down to idle. And the metric is transactions per second, and the measure that you use is system power, which you can easily transform into energy. And we're running this on a quad-core, 8-threaded Intel Haswell server, whose number I don't remember, but I can look it up if you care. Okay, so what is this model? Okay, so remember, they said, look, the most energy efficient point is at max utilization, right? So we're going to run this thing full out, and so that's 100% down here on the x-axis, and that's going to dissipate some amount of power, right? So 110 watts or something like that. Okay, and so then what we're going to see is that as we go to lower loads, we're going to get less efficiency, but of course we're going to use lower power too, right? So what energy proportionality says is, well, the work that you do should be proportional to the power or the energy that you're putting in, right? And so what you'd like to do is see this perfectly proportional line from at no work I should not spend any energy all the way up to that most efficient point. Okay, that's energy proportionality. Really simple concept. Okay, turns out it's impossible to get, right? And that's impossible to get because when you get to 0%, unless you're smart, you're still burning a whole bunch of power because you haven't turned it off yet, right? And this, you're not allowed to turn it off, okay, in these experiments, right? Because we're worried about real-time response. If Google had to power cycle up when you want to do a search, that's not going to work, okay? Okay, so in this particular Haswell chip, we burn something like 27 or 28 watts when we're doing nothing, okay? So, right away you can see that achieving true energy proportionality is never going to work, okay? And so that's where this other notion, which I blipped by on the previous slide, came in, which is this dynamic energy proportionality. And that's basically saying, look, you can't get rid of this or completely get rid of this idle power. So, that's what you get at 0. Then the best you can do is be linear all the way up to this peak performance point. Real simple, okay? And so, well, how well do we do with that? Well, so at the time they wrote this paper, and I was trying to put a graphic in here, but I could not make it work. And I didn't want to bug my graduate student to make yet another slide for me. But see, you get old enough, your PowerPoint skills atrophy. Plus, it's a new version of PowerPoint for me. But the curves kind of looked like this in the original paper. The paper that introduced this notion of dynamic EP had curves that were, up here somewhere in this what we call the sublinear zone, because not as good as this linear dynamic EP model. Okay, but Intel read these papers and they said we can do better, and they did better. Okay, so Haswell is a fairly recent chip, and here are the other data points that we get from Haswell. Okay, and they're pretty close to this ideal line. Okay, and so this is where I say they did a great job. This metric was really good at influencing the designers at Intel and elsewhere in improving the behavior of their chips on these important workloads. Okay, and there's very few points up in this sublinear zone, and they're not very far up in this sublinear zone. Yeah. Hold your breath. Okay. Yes, you're about to see that curve, but let me give me like 4 more slides to get there. But yes, we will see that. Okay. So this is sort of your classic power performance graph, and how this is usually visualized. The other way to visualize this is to look at the energy efficiency. So again, looking at these, what I'm calling the conventional servers, the servers that Barroso and Ho were worried about, and really up until Haswell, that you've seen different behavior. But so if you look at the energy efficiency of energy proportionality, what does that say? Well, if we have this ideal green line, irrespective of the load, we should get the same efficiency, right? And so that's great, but of course that's not achievable. And so this curve is what we get on Haswell, and the dynamic EP, as we saw, was close to that. So that line would be pretty close to this purple line. But it's not green, right? Again, you still get crappy. By the time you get to 0 load, you have no efficiency because you're still burning power. You're getting no work done, right? So you still get this lousy behavior. Okay. Okay. One more slide here on more conventional wisdom. These are basically just more papers reiterating the points about energy proportional. Is the gold standard. We don't need to do explicit power management, as power consumption varies naturally with utilization if we're energy proportional. Okay, we realize we probably won't be perfectly energy proportional, but maybe if we were close, right? And then ideally systems would exhibit energy proportionality, wherein servers consume power in proportion to their loads, and modern servers are only maximally efficient at 100%. Okay, so all these conventional wisdoms, which we're already forecasting, are not going to be true. Okay, so why aren't they true? Okay, they're not true because current systems, some of you may have noticed, if I jump back a second here, this purple line was called peak performance configuration. You could also call this default configuration, right? The way when you boot up Linux, this is what you get, except, well, there's like a couple different releases, but this is what most releases will give you. Just a default configuration, run at full speed, go to turbo boost when it thinks it should, and don't do anything special. Okay, and so you'll get that behavior. Okay, but that's not the only behavior the system can do, right? There's all kinds of resources that these systems have. Okay, we can do dynamic voltage and frequency scaling. So what this means is we can change the frequency that the processor runs. That allows us, if we slow it down, we can then reduce the voltage and run at the lower voltage. That'll dissipate less power. Okay, so we usually actually set the frequency, and then the voltage follows that frequency. We'll run at the lowest voltage that we can for that appropriate frequency. We can also, we have multi-cores, so we're running on a quad core. We could run on 1, 2, or 3 or 4 cores. Okay, these are hyper-threaded cores, so we can have 1 or 2 threads per core. The processors do prefetching. We can turn that on or off. If Intel would let us, we could get inside and turn that knob even more, like how far forward we should prefetch. There's all kinds of knobs in the microarchitecture, most of which we can't touch. Intel can, but we can't. Okay, and then there's actually been some, there's been a lot of research on varying the cache size, and Intel is now allowing you to play some games to manage the cache size, although not as many as I would like. And there's lots more possible knobs. So the net point here is that if we play with these knobs, we can have multiple different configurations that can serve the same load. Okay, and those different configurations are going to have different power and energy consumption properties. So I'm going to show you a bunch more graphs. The only knob I'm going to turn is the dynamic voltage and frequency scaling knob, at least until I tell you otherwise. Okay, so this is the same graph we had before for our Haswell system, and now we're going to turn one knob. Okay, and we're just going to turn it one notch and leave it. Okay, so we're going to set. So this configuration is the peak configuration. This knob, we have fixed the frequency to be 3 gigahertz. I think the peak frequency that you could set this one at was 3.5. And then processors have this notion of turbo boost where they can run for some period of time at a higher frequency. And they do that sort of automagically. And so in this case, we fixed the frequency to be 3 gigahertz. Okay, and then we run our spec workload again. Okay, and what happens? Okay, well, what happens is we get some different data points. Okay, and the thing that should be leaping out at you is we're doing better than the linear, which was sort of the best we thought we could do given non-zero idle power, and in fact we're doing better than EP. We're doing better than this ideal energy proportional that we thought we couldn't do better than. Okay, and so right there should be motivation to say we need to revisit what our metric is. Okay, energy proportionality should not be the goal, right? Maybe it was a good goal before, maybe it was a good metric before, but it's not a good enough metric. Okay, so let's look some more at what kind of a metric we might want to have. Okay. Well, but the question is, the question is, what is your objective, right? And it is. So we'll get to how to reason about optimality in a couple of slides. Okay, but you're right. I mean, there is, so this particular workload is a throughput workload, and so long as you meet your throughput goal, then that's all you need. And there's plenty of applications like that. So like speech recognition is a classic example. So you need a certain rate of work to be able to do a certain quality of speech recognition, and it's not going to get any better if you do it. You run faster, you're going to be done sooner, right? And you only need to do it at a certain rate. Speech is only at a certain rate, right? And so there's things like that. There are, if you start getting into response time issues and service level agreements, then things get harder, and I've got a couple slides at the end. We don't have all the answers there. We're doing some work on how to answer those, but there's a lot of possibilities in terms of how to address that. But I mean, this business about saying, being down here, you're 10%, you've got 10% offered load, and you're running here. Well, you don't need to be here, as we'll see in a minute, or 20%. We don't need to be here. There are better points to be at. Okay. So let's look at some of those points. Okay. So up here we talked about the sublinear because we weren't as good as that linear dynamic EP. This we call, it's not really a very good name, but we call it super proportional because it's better than energy proportional. Okay. Yeah.
Do you have a feeling for, say, what Google would say when that your blue line intersects 100%, 10% below? I mean, what does that mean for Google's, business to be 10% slower than they are?
Well, I mean, I have talked to Luis Barroso has read this paper. I've talked to others at Google and Microsoft about this. The thing that they are worried about and that we have not completely addressed is, what is the impact on tail latency, right? The thing that, all Google cares about is tail latency, right? What is the latency of the 1 in 10,000 query, right? And they want that to be short. They want very predictable, maximum latency, maximum response time. And we don't have all the answers to that. There's some work that Ed Bouillon at EPFL has been doing, in fact, I'm going to be at EPFL in the spring for 2 months, and we're hoping to use some of his stuff with these models to see if we can't, get closure on that. But I mean, that's clearly what they're worried about, right? And the issue, but the thing is that you're down here. You don't go from here to here in a nanosecond, right? And it doesn't take very long. It's a small number of milliseconds to go from configuration here to that configuration, right? And so long as you can respond, you can detect the problem. The real problem isn't changing the hardware. The real problem is detecting that you should soon enough, right? And that's a software problem, not a hardware problem. I agree. There's lots of interesting problems, right? And this is I think this is going to open more problems than it's going to solve. But my goal is to we'll get to the new metrics in a minute. But my hope is that the new metrics will actually help guide what we do next. Okay. So we had 1 point fixed for 3 gigahertz. What happens if we fill in all the other points that we can get just by turning the DVFS knob, right? There's other knobs that we can turn, but we're not turning them now. And what you can see is, there's a lot of points, right? And most of them are, or almost all of them are better than this, this dynamic EP linear line, and a lot of them are better than this ideal energy proportional line, right? They're in that super proportional zone. Yeah. Transactions per second. Yeah. No, it's throughput. So this is basically saying what fraction, 100% is the peak throughput that this system can do under anything, right? And then this, this point here is, 36% of that throughput, right? And so if you know that's the throughput that you want, you probably want to be whichever point it was I pointed at, that one right there, okay? Okay, well, why did I pick that point right there? Well, I think most of you are probably familiar with the notion of Pareto optimality. And so, the idea here is that, Pareto defined this concept of Pareto optimality, the Pareto Frontier, and it's the set of points, the subset of the tuples in that state space where you can't, in this case, can't increase the performance without also using more power, or conversely, you cannot reduce the power without also decreasing performance. Okay, and you can prove, or Pareto proved, that you can, that all of the goals that you want to satisfy, minimum energy, energy delay product, ED squared, lots of possibilities here, they're all going to lie on that frontier. Okay, so that says that we always want to pick a configuration that lies, if we want to be optimal, on this frontier. Okay, we never, all of these interior points, they're dominated one way or the other, right? If we were running at this point, okay, we could get the same throughput but for lower power here, or same power, much higher throughput over here. Okay, so you always want to be on that Pareto frontier. Okay, and in fact, if you had your druthers, the place that you'd really like to be operating at is this point right here, because this is the point that's going to give you the optimal energy efficiency, right? The most work for the least power, right? And if you move anywhere else, that ratio will change. Your energy efficiency will decrease. Okay, so we want to be at that point. So the new, okay, so whoops, getting ahead of myself here. So if we go back to the energy efficiency slide, so this is the conventional energy efficiency slide that I showed you a couple minutes ago. This is if we add in all those other points and the Pareto frontier, right? Well, this was, EP said this is our 100% perfect efficiency, but once we get up here on the Pareto frontier, on this half of the graph anyways, we're better than that, okay? And we're actually quite a bit better than that, something like 27% better than ideal, right? That's pretty good. I'll take that, Okay, and so that's, we again talk about that region as the super proportional region, and again, the place that we would like to be is, up at that optimal place. Okay, so, what's the problem with the old EP model? Well, it's obviously not ideal. We can be better than the best. Neither EP nor dynamic EP is ideal and clearly not optimal. So we need new ideals and new metrics. Okay, so that's our goal, and we talk about having two. So just let's see. So we're going to talk about new ideals, then new metrics, and then management. So where's my clock here? Yeah. Sure. Mm-hmm.
So what you're telling me is that I should go down to only 65%.
No, I'm saying if you did, that you would be more energy efficient,
But
right?
I still have 35,000 transactions.
Yes, but
that I need to run. So I'm going to have to buy another server that I'll probably be running at somewhere else.
well, okay. So I'm not going to answer the total cost of ownership management for a data center. That's an interesting question, right? But
Even from an energy point of view, I still have that load that I need to run.
yes, but so the thing that you have to realize is that when you configure these big data centers, you are configuring for peak load, right? And so, and they don't operate anywhere near peak load very often, right? And so if you've got a bunch of servers, which you're already paying for, so don't count the capital cost in there, how many of them should you have turned on, right? And so what I'm saying is, well, okay, suppose I got a bazillion, I need to have, 100,000 servers to max your load out, full out at what was the peak thing, right? And it's like, well, okay, but I have 1 million, so I can now say I'm going to drop these down to run them at 2/3 efficiency, and turn on another 50,000. I'm going to run 150,000. They're all going to run at 2/3 if I did my arithmetic correctly, right? And it's going to be 27% more energy efficient. Okay.
But in Tom's case, you can look at what the 35%, because he's got 35% left when he's doing 6/3. You can figure out where you are on the Pareto frontier and ask the musical question: is the combination of those efficiencies more efficient than running at peak power or not? Right? I mean, you can actually figure out for his extra 35% workload,
Yep.
whether the sum of these two things, or the average of them, I guess, is less than running at peak or not, and just pick whichever one's more energy efficient. If you're only interested.
If it's only energy, you already have the machines, and it's just a question of how many do I turn on, you're always going to be better off operating here.
You have to buy a second machine.
If you have to buy a machine, then you have to do the whole total cost of ownership thing.
But if I don't care about cost, I just care about energy efficiency. If I buy a second machine, I run 35%
I see what you're saying. Yeah. Well, I mean, if you're just saying run all out, and I have to buy another machine, run them at 50%, not worrying at all about latency, right? Then I drop to 50% energy. It's going to be more.
5% left, which is to your left a little bit on that frontier. And so now you can figure out, is it worth it? I mean, you have the answer. It's just,
Exactly. Well, I mean, my goal is ask the questions, right? You know, so. Well, the only qualification I would say is, I want to turn on enough machines that all the machines are running at this point, right? And then all the rest should be turned off, right? I agree with that, and that's. Oh yeah, you would never. I mean, and in practice, the problem is you're mostly down here, right? I mean, there's a whole nother. Well, we'll get to load management. Well, maybe we won't at this rate, but I have a slide that at least says there's a problem here. So let me, since I think I'm supposed to be done in 25 more minutes, 20 minutes, holy cow. Let me move forward here. So basically, if you think about EP and dynamic EP, they're really different types of ideals. So EP is a design ideal. It's to help an architect come up with a more efficient machine. So for example, EP was a driving force in getting Intel to drive down the idle power in their servers. Okay, but once you've built the machine, you're not going to get the EP, right? So dynamic EP is what we call an operational ideal. It's the best that this hardware can do, and you'd like to do the best that this hardware can do. So something that the operating system or system operator might think about, load management, in a data center. So we want both types of ideals, and so we're going to introduce two. The first is this design ideal, which we call energy optimal proportional. So ideally, we're operating at that optimal point where we have the maximum energy efficiency. And so, this is the best we could do, irrespective of the offered load. And then, okay, not probably going to be able to achieve that in practice. So we need some sort of a dynamic energy optimal, the equivalent of dynamic EP. So what is the best that we can do for the given hardware? Well, it's to stay on that Pareto Frontier. And so that's going to be our operational ideal. Okay, so this graph is showing our conventional ideals along with the Pareto Frontier. And so we got these two new ideals. The first one is this EOP, or energy optimal proportional. And it basically says, well, in a perfect world, right, we would get, for this hardware, we would get this efficiency irrespective of how much load we're putting to it, right? We're not going to get it, but at least that would be our ideal, right? And so we should be aiming for that, right? And then the second thing is our operational ideal. So that is dynamic EO. Well, guess what? That's just renaming the Pareto Frontier, right? The best we can do is to be on the frontier. That's our goal, okay? Okay, so then this slide is just comparing these different ideals and the relationships between them. And dynamic EP is always less than or equal to the efficiency of EP, which is also less than or equal to the efficiency of EOP. There's not too much. I'm going to skip that. I think the sort of philosophical thing here is that EP was sort of, people were equating that with optimality. And it's not. They're not the same thing. Optimality at every load implies proportionality, but the converse is not true. Okay, and EOP is optimal and therefore is proportional, whereas EP is proportional, but as we've seen, is not necessarily optimal. Okay, so now let me get to what I think is the most interesting part of this talk. So let's make sure I have time for this, and that's the new metrics. Okay. So this is back to our slide with the little blue thing, which I already disappeared too quickly. There it goes. There's our useful work. Okay, so we've got PUE is the ratio between the total facility energy and the IT energy. Okay, and we need some kind of a metric that's going to quantify the IT energy to the useful work. Okay, so to those blue blobs that are flowing out here. And so that metric is something we're going to call CPUE. Okay? So CPUE is the computational power usage effectiveness. And it's a direct steal from PUE. And we're trying to quantify the waste in the computational energy. Okay? So what is the actual IT energy that we are consuming, we're feeding into those servers, divided by how much energy we would use if we were operating at the EOP point, right? If we were at our energy optimal point. And of course, this is normally has to be greater than or equal to 1. And we've already seen that it can be quite a bit greater than 1. Okay. Now, so this is sort of the conceptual thing. CPUE depends upon the configuration, depends upon the offered load, right? And so we're going to talk about that in terms of the configuration and the load. So it'll be the actual server energy for the configuration they're running at with that load, divided by what is that optimal energy. Okay. And so if we look at what is the energy that our computation does, well, it's going to be the CPUE factor times the minimum energy that we could be using to do the same computation, right? And so, of course, to the extent that it's greater than 1, we're going to be wasting energy. Okay, so that's the base metric. But the metric, okay, so let's just break that down a little bit, and we're going to factor this out. Okay, so CPUE is this ratio of the actual server energy to the optimal energy. That's this, symbolically ECL over E min, and then we can normalize that to energy efficiency and get us to eta max. So this is the best efficiency we can get. That's that one point we were talking about before, and then the actual efficiency that we're getting for the given configuration and load level, right? And then we can factor that by just multiplying through by the efficiency on the Pareto Frontier for a given load, okay? And then these two terms are what we're going to call the LUE and the RUE, okay? So this is the load usage effectiveness and the resource usage effectiveness, okay? So, and this is going to lead to what I like to call the iron law of energy efficiency. So before I explain why I call it that, let me remind you or teach you about the iron law of performance if you haven't seen this before. So I think this is, I was trying to remember whether this is Joel Emmer and either probably Doug Clark, but I can't remember, I needed to look that one up. But this has been in every textbook, architecture textbook for the last 25 years. And so, what we care about is, if you're building a computer, is, how fast does it run a program, okay? So time per program. And so we always want to just, minimize this, right? But when you're building hardware, it's extremely useful to think about, well, let's factor that into these 3 components, right? The instructions per program, the cycles per instruction, the time per cycle. And of course, the cycles and the instructions cancel out, so it's the same thing. But by factoring it this way, it helps architects and software designers to reason about where I can improve the performance of the system, right? So how can I improve instructions per program? Well, I could get a better, write a better compiler. I could change the instruction set architecture. I could change the algorithm so it needs fewer instructions, right? Cycles per instruction, well, I can pipeline my processor. I can add a cache, add a predictor, do out-of-order execution, all kinds of stuff, right? There's thousands of papers that basically focus on CPI. And for time per cycle, I can look at my technology, my circuits, my pipelines, whatever, right? Lower level issues. And of course, there's interactions between these. They're not totally independent. Nonetheless, this is an incredibly useful way of reasoning about, how to make time per program better. Okay, so that's the motivation for the iron law of energy efficiency. So, we can factor the energy it takes to do our computation at a particular configuration and load, right? We can factor that into LUE and RUE and, of course, the minimum energy to do the computation. So this is, I hope, and my goal is to say this is what's going to help us to focus the designers' attention into how we can reduce that energy. Okay, so LUE says, well, the load usage, the efficiency really depends on what load level we're operating at. If we are at a low load, efficiency is pretty hard to get, right? Resource usage effectiveness says, well, you really, for a given load, you want to configure the system to be as efficient as it takes to provide that load. And of course, E min, well, it's not really min. It's the min that this particular hardware can do, right? And so there's a whole bunch. I mean, this could probably be factored many more times, but I haven't gone there yet, to say what else can we do in the processor and the system to do this same computation with less energy. Okay. So I'm going to focus on these two things, but I think there's actually a lot of work that could be done there. Okay, so let's look at LUE. So LUE is just the, so this graph is showing the CPUE. So this is the ratio of the utility of the IT server over the best that you could do. And it's as the load varies. Okay, and so this is saying, if you're operating at really low load, you're going to have really bad CPUE, right? If you're not doing anything, it's going to be infinite, right? So, and even at 10%, it's something like 3.5 or something, 3.5, I think. And the best that you can do is to operate up here in this, 67%, wherever that is. Okay. So the good news here is that there's a pretty wide band out here where if we can stay within that band, we're going to lose less than or equal to 10% of our energy efficiency if we can figure out how to keep our servers this busy. Okay, now this is still a hard challenge because most servers are probably down here somewhere, but that's I view this as here's quantitative data that says you need to be over here, right? So focus on ways to get over there. Okay. Okay, so that's LUE. RUE is the research usage effectiveness. So this is the piece of that says how much energy or efficiency are we losing because we're for any load we're not operating at the right point. So if we're let's just pick this point here. So what 30-ish%, 35% or whatever, right? And if we're operating at the peak, the peak configuration up here, peak performance configuration, we're losing 45% of our energy, of our IT energy, just because we're misconfigured, right? If we were smart enough to pick that configuration, we would say 45%. Okay, even at this pretty low load, we're still losing a lot due to LUE down here, but at least we could save that 45% due to RUE. Okay, and so this says, well, great, I would really like to be configured down here, instead. Okay, and there's an awful lot of points down here that are, within 10% of the ideal, right? So maybe I can't always get down here at the ideal configuration, but I don't really have to. I don't mind losing 10% here and there. It's the 30, 40, 50% that really start to add up. Okay. Let's see. So just to recap, non-optimal loads mean that LUE is going to be greater than 1. We're going to waste energy there. RUE greater than 1 means there exists a configuration that uses less energy but can serve the same load. Okay. So since I'm almost out of time, let me jump ahead here. So load management is a hard problem. We don't really have any answers to this. I think there are many. It's an inter-server problem because you need to decide, how many servers do I need to have active? How do I distribute the load in a fair way? What if they're stateful? There's very hard problems here. There is some possibility that you can frame this as an optimization problem. That's the easy part. The hard part is how do you build the software systems to do the load balancing. Okay, the part where we have some results are in the configuration management. How do we pick a configuration for a given load so that we reduce RUE, so that we operate near that dynamic energy optimal point. This is something you can do within a single server, so it's a lot easier to manage. And it basically involves turning different knobs. Now, there aren't that many knobs. DVFS is the obvious one. There's a couple of others. Linux actually tries to do this. Turns out it does a really, really piss poor job. Okay, it is next to useless. I mean, there's really only 2 knobs that do anything. One of them basically puts you at the peak performance all the time. and the other one puts you at the lowest possible frequency all the time, neither of which is what you usually want. Okay, and we have lots of data on that, which I won't show you. So what you need is a reactive governor, which is going to turn those knobs for you. And I will, let's see, how am I doing on time? Not too well. Okay, so basically it's loosely inspired by Ethernet, trying to do with the exponential backoff and trying to pick the right frequency to run. And basically, so graphically, let's see if I can do this animation here. Time flowing on the bottom, so we run for 10 milliseconds with prefetching turned off. So PF is for prefetching. The red means it's off. We turn it on, and we run for another 10 milliseconds and measure that again. We now compare to see whether prefetching helped or hurt. Surprising how often prefetching hurts. And then we look at how many cycles in the last period did we actually execute versus were idle. And then we use that to calculate a target frequency. If the target frequency is slower than our current frequency, we just set down to that. If the target frequency is higher or equal to us, we don't know how much higher it should be. We're busy all the time. That's where this exponential backoff thing kind of comes from. We go up a step, and the size of the step doubles each time. Okay, so and then we run for the rest of our interval and then repeat. Okay, so this graph is showing what that governor goes if the period is 50 milliseconds. So 10 milliseconds, 10 milliseconds, and then 30 milliseconds. Okay, and so what you can see from this is, we're sticking fairly close to this dynamic EO Pareto Frontier, and holy cow, we're doing better. Okay. Okay, why are we doing better? Well, it turns out there's two knobs. I don't remember if I told you we had two knobs. There's two knobs that we're turning. One was the DVFS, obviously. That was the main knob. But then there was that prefetcher, right? So turns out for this workload, you don't want the prefetcher on all the time. Turns out you want it on some of the time, but not all the time. So just turning it off doesn't get you there. You need to be dynamic about it. I'm not entirely sure why, but you do. So you actually get something like 5% better than 100%. Throughput, which was kind of surprising when we first saw that. It goes away if you get rid of the prefetch stuff. Okay, so we're sitting pretty close to there. And if you look at what's the RUE for this, then we're sitting within 5, maybe 7% of the best of optimal here. Could we get closer than that? Well, the answer is yes. If you boost this the time interval to 5, so basically. The problem, the reason we're not right on this frontier, the main reason we're not on the frontier is we're running 10 milliseconds with prefetching on, 10 milliseconds with prefetching off, and then the other 30 with whichever one was best. So 20% of the time we're doing the wrong thing, right? So basically what 500 does is it says, well, you're going to make your guess and you're going to run that for longer. The overhead's going to be less. And in general, that's better, even though you're not checking quite as frequently. Okay, and so you see we can move down just a little bit closer to the ideal. But, I think the real takeaway isn't we're a little bit better down here, right? It's like we're a lot better up here than up here. We're not up here, we're way down here. So we're saving 50%. And by the way, this is, this is energy coming out of the wall, right? There's a energy meter, power meter that's measuring, how much energy we're consuming for this. Okay. Okay, so let me just finish up with things we haven't solved, and we've touched on some of these. We have just dealt with throughput. Okay, throughput is one metric that people care about. We have not dealt with response time. A lot of service level agreements or SLAs, deal with response time. Simple ones like maximize the energy efficiency we can do. Maximize performance under power cap we can do, things that say, make sure that the 99.9% of all the queries complete within 200 milliseconds. We don't have that yet, okay? But there's reason to believe that you can still meet those goals and still operate not at the peak configuration. But the key question is how to detect soon enough, when you should respond, right? And the kind of thing that we were doing with our reactive governor is unlikely to be sufficient to do that. So we have some ideas, but we're not there yet. There is some suggestion that actually Intel may be working on something similar. They're doing this. So Skylake is sort of changing the way they handle power management. And they basically have a separate power controller that's integrated into the die, which appears to be changing at least the DVFS knob. We don't know if it's changing any of the other knobs, but they should. And I'm hoping that maybe some of this data will help convince them that they ought to do that too. So there's a bunch of challenges. One of the classic challenges is you want to do system power, we can do measurements from the wall with a power meter. That doesn't help a running processor very well. And so how can you estimate that? So it turns out actually you can do a pretty darn good job using simple regression models to fit wall clock power or wall power to the RAPL counters. So the RAPL counters are the counters that are integrated into Haswell and future parts, and you can basically make a prediction of what the power dissipation is, and then either do a linear fit or a quadratic fit, and both of them are pretty darn good. So, I guess just to wrap up, I hope I've showed that the conventional ideal models are no longer adequate. EP does not imply EMIN. I introduced these new ideals, EOP, energy optimal proportional as a primary design goal, and dynamic energy optimal as the primary operational goal. Introduced new metrics, CPUE, the computational PUE, load usage effectiveness, and resource usage effectiveness to help focus the attention on where to optimize future designs. And we have lots more work to do. So I'd like to acknowledge my student, Rathajit Sen, who did most of this work and certainly did almost all the slides on a very short timeline, and then grant funding from NSF, and disclose my interests, financial interests in AMD and Google, both of whom support me independently and my research. So I'll take any last questions.
Hi, Professor. It's just a record. Okay, sure. So I'm just wondering, like, if the heterogeneity of the system would, somehow impact this Pareto Frontier, because in this talk I can see, like, would GPUs or accelerators, help in this case?
So that's a great question. So future systems are increasingly heterogeneous, GPUs and different types of accelerators. I guess in my view, what a GPU would do is potentially reduce EMIN, and say, we can do this particular computation more efficiently, use less energy to get that. But assuming the GPU has the same kinds of knobs, the same DVFS, a bunch of them don't actually have it, but they're moving in that direction. So assuming you have knobs, then you should be able to apply this in a pretty direct fashion, I would think. But to be fair, I haven't really thought about it, or certainly haven't experimented with it.
So you said that you could apply some operating system hints
Mm-hmm.
to kind of guide some of this.
Yeah.
What else could we software people at a higher level runtime who are able to introspect
Right.
application performance do to be ready for these types of changes coming down the pipe?
Yeah, so that's a great question. I mean, I think that certainly as an application designer, whether your workload is only throughput, sensitive or whether it is response time sensitive. And a lot of times there's phases, where things matter, and one thing matters versus another. I think that there definitely are opportunities there to provide hints, either to the operating system or perhaps even directly to the hardware. I think one of the things it's not clear, they haven't published anything about Skylake. I mean, we had a paper that we had never got published. We kept saying, oh, everybody's doing this. It's like you look around for papers, like nobody's doing this yet. And it's like you find out, I'm pretty sure Intel was doing it on Skylake, but they hadn't published anything, and they still haven't published anything. And it's like, how do you reason about all these different knobs, finding the Pareto optimal frontier, and then what is it that the workload cares about, right? And capturing especially the more complex SLAs. It's I mean, tail latency. But flip side is, if I know what the application structure is, I can do a queuing network model, right? And I can use that queuing network model to inform these decisions about what the throughput of the servers have to be, and do bounds on latencies. And I think that's that sounds like a pretty cool thing to try, but it's going to require knowing something about the structure of the application, not just. I mean, Skylake is it's a controller on your die, right? It's not doing anything about system level decisions, which I think is where the real value add is. So I don't know if that really answers your question, but.
I had a question about in terms of providing more knobs for the software people to be able to, explore that space. One of the just commercial concerns I've heard is that
Validation?
Well, there's validation. I was going to skip that, but also in terms of performance, one of the things that they're oftentimes very concerned about is actually putting out a new processor which actually will do worse on any given application, and the sort of embarrassment of like, oh, you put a new processor out, but I want the old one because it actually performs better for me. I mean, have you thought at all about sort of the space amongst different applications and how they actually respond to these different controls, and whether they're robust or whether it's kind of fragile based on the application?
I think the correct answer is I haven't thought about that very much. I mean, we have thought a little bit about the validation problem, and I think for certain things, what they're doing with Skylake makes sense because, I mean, exposing internally they have, there's a register that says how many prefetches should you have outstanding under certain different circumstances. Exposing that to the user, I can think of all kinds of ways that you can make that thing not work, and and they can't possibly test all of them, right? And so, from a validation perspective, they're never going to expose that, and they shouldn't, right? The question, what they're trying to do is say, well, what can we expose that will allow us to make sure that we only do things which we have validated that to work, right? And so there may be some things sort of in that direction where they can say, well, we're only going to let people do this, and maybe they can protect themselves a little bit. But to some extent, yes, I know Intel hates this problem, but they've lived through it before, and I also think it's sort of this notion of, I mean, there's also this notion that computers never get slower as they get older, right? It's like, well, that's not life. I can tell you, I'm a lot slower than I was when I was younger. I don't understand why the hardware should be any different, and we should just deal with it, right? Your television, the pixels get fuzzier as they get older, right? It's not just your eyes, and so, it's, I think that, we should just live with it, right? And we should embrace it and just like, okay, so my processor gets a little slower, maybe one of the cores dies and the thing keeps running, right? I think that's the future for hardware. I mean, Intel doesn't like that because they want you to replace it as soon as anything goes bad. But I think in the long run, that's not going to be the way things work. So, yeah.
So, get back to your SLA problem. One thing that I noticed is that, your graphs assume that each of those data points is a point. When you're at 80% load, but as a distributed systems person, nothing is the same twice, right? That's a distribution to me. And so, have you thought about turning it into a monitoring problem, right? The problem you have if you want to turn those things into distributions is figuring out what's the distribution at each point. And then you could take the quantile, the 99th percentile or whatever, and then draw your graph against that. But now you've transformed the problem into how do I get a distribution of
Right.
things that's reliable at each point? And that's potentially that's potentially a measurement job. Right? Have you given any thought to what it would mean to build better instrumentation?
Yes.
So that you could apply this technique almost directly just by...
We have given some thought to it. I mean, the challenge is, well, we don't build chips, right? We simulate them. And it's really hard to simulate these kinds of problems, right? And, so, I mean, we've done some experimentation with that. But it's hard to get compelling results that you stand behind when you can simulate a fraction of a second, right? And, I mean, even 50 milliseconds is a lot of simulation time in a detailed architectural simulator. So that's where this gets to be a challenge, right? And it would be great if we had, if I could get, have FPGAs to customize, counters and stuff like that, but that's not the real world anymore. So, but I'd be happy to talk about it some more. I mean, it's something we've thought about. So, or more we've sort of talked about talking about it as opposed to really think hard about it. Okay, well, I think it's way past time, so we'll let the students escape. So.